All right, all yours.
Cool. Welcome to the talk, everyone, and welcome to Amazon campus for the first time. I'm Asad Jawahar. I'm a development manager at Amazon Web Services, and I work on the Amazon Simple Workflow tool. And specifically, I'm focused on the developer-facing features that we provide in the Simple Workflow service. And that includes a number of client libraries that you use to build applications for Simple Workflow, including a Java framework that you can use to build distributed workflow applications for Simple Workflow. Simple Workflow provides a number of very unique features and capabilities that allow developers to take the backend processing of their applications and distribute and coordinate it across multiple machines and multiple components. And it does it in a way that allows you to write code that's fairly straightforward for you to understand. It's pretty similar to the code that you are used to writing. And at the same time, the code is much more maintainable. There's a lot of boilerplate that Simple Workflow and the Flow framework does for you. So in this talk, I'm going to give you an overview of the service. Then we're going to do a bit of a deep dive into the Flow framework, which is our Java version of the framework. And then I'm going to walk you through like a use case and see how that can be implemented so you have a better feel for how the framework works. So quickly go over the outline. First, I'm going to talk about why you need to distribute work, how that helps us in our applications, overview of the service and Flow framework, look at a use case. And then since we are all Java developers here, I'll go under the hood a little bit and talk about how the framework itself works. We usually don't talk about it, but since for this kind of framework, this will be interesting. It's a pretty extensive framework, so I'm going to take a couple of interesting areas that are kind of unique to this framework. And then wrap it up with some of the lessons that we have learned with our experience in building this framework. Okay, so Simple Workflow is a service that was launched as a public AWS offering only last year. But really within Amazon, we were using it for a number of years. And the reason that we built this service was to address a need that we saw becoming increasingly common in the applications that we were building within Amazon, and also that our customers were building. And the need that we saw was that these applications were trying to coordinate work across a lot of different components that were running on multiple machines. And there are various reasons that you want to do that. The most obvious one is scale. Right? If you want your applications to be responsive under load with a lot of scale, the easiest thing you can do is take all the heavy lifting out of the code paths that the users interact with and have it performed in the background asynchronously by our fleet of machines. So that's what a lot of these applications did. The other interesting thing about these applications was that they were using a lot of components which were existing. They pre-existed somewhere. They had some legacy system, maybe running in their private networks. So that added another kind of set of challenges because now you depended on another system which you didn't fully control. You typically had lower reliability, so you had to deal with a lot of kind of error conditions. And a lot of times you would deliberately have these components running on separate fleets of machines because you want to be able to selectively scale them up as you find bottlenecks in your system. Another interesting aspect of these applications is that the background processing that they do is really a multi-step process. So there are some kind of obvious solutions for doing a single atomic fire and forget kind of tasks in the background, but typically these applications did processes that were multi-step and that ran for a longer period of time. So an example here is that user registration. When you register a user, you may want to do a fraud check on the information that they provided. You may want to validate their credit card. And when then both the checks pass, you send them a confirmation email. So that's a case where it's multiple things that need to happen in the background and then you combine them another thing needs to happen. And like I said, some of these tasks were long running. And long running here is relative. Some of these were multiple months long. And of course, you have a need always to run tasks in batch. Typically, there's a data set that you need to process at a specific time of the day. You want to shred that and run that on multiple machines. And there's also the need of periodically running some tasks. So there's distributed cron kind of aspect to these applications as well. Now, building these types of applications can be quite challenging. You need to make significant investments in the infrastructure to distribute and coordinate work across a bunch of different components, a bunch of different machines. And that typically requires you to have infrastructure to create tasks, assign them to the components of your application, track their progress as these tasks are ongoing. Your application needs to know where it is in its overall execution. So you need to store the distributed state of your application somewhere centrally where the application can go and authoritatively tell what's happened so far, what to do next. Failures happen all the time in distributed environments. You could be talking to a different system in different kind of network situations. So you need to be able to handle those failures. Workers may die. They want to implement different kinds of remediations. Networks are unreliable. You may lose messages. So you need to make sure that your tasks are executed only once. And typically, these types of hand-rolled solutions are built with databases and queues, and those typically don't scale very well. They become bottlenecks pretty quickly. So Simple Workflow was designed to kind of solve that problem. What it provides is a coordination engine in the cloud that allows you to, that allows your application to model asynchronous distributed interactions. Your application goes to Simple Workflow and create a task for its components. Simple Workflow holds on to that task and assigns it to the component when it becomes ready. Under the covers, Simple Workflow is using reliable messaging, which ensures that the task is only ever assigned once you are working. So there's no duplication of work. Simple Workflow also acts as the repository of state. And by state here, I mean the execution state, how many tasks are ongoing, which ones are completed. So it's not your application's data, but your application's state. And since it's this state, the repository, the component can go and ask for the current state, your components themselves can become completely stateless, which means they can easily scale. Your workers or components talk to Simple Workflow through a holding mechanism, which means they only ever need to make outbound calls. That means they can be hosted anywhere. Scaling is as easy as adding more worker machines that hold Simple Workflow, and the traffic that's coming through will naturally get load balanced across all these machines. Failure handling is explicitly modeled in Simple Workflow. We'll look into more details of how that's done through the flow framework. The state that's stored in Simple Workflow is replicated, and we make sure that there's no loss of state. So that means that even if all the components in your application go down for some reason, you can bring them back up. They can sync their state back from Simple Workflow and keep progressing from where they left off. Simple Workflow, the execution state that it's maintaining is actually a detailed step-by-step record of what's happening in the application, including all steps and decisions that you make. That's sort of very useful for auditability as well. So it's not only useful at runtime, but an operator can go and look at that history and try to figure out what has happened in the application. Or a developer can use it for development purposes. Okay, so let's talk about some of the key concepts, and then we'll look at a real example. And it's probably best to kind of look at Simple Workflow in the context of a real use case. So imagine you have an application where a user goes and uploads a bunch of images, and the application then goes and creates a thumbnail for each of those images. So ideally, you want to have a lot of these running in parallel, so you can quickly process all those images. But if you look at the processing of a single image, it's a simple three-step process. Your application is going to download that image. In this case, I'm saying it's stored in S3. It creates a thumbnail for that image, and then it uploads it back to our storage. Now let's see what that translates to in terms of a Simple Workflow application. So there are a couple of core concepts in Simple Workflow, and it's called the activity and the decider. In Simple Workflow, an activity is a single step in your process. So in my example, the 3 boxes, each one is an activity. Right? It's a single atomic step. The decider, the green part down there, is the coordination logic for these activities. And in this case, the coordination logic is very straightforward. It's a sequence. So I run the first activity, when that completes the second, and so on. But you can imagine you could have any level of complexity. You could have a state machine, decision tree, what have you. And if you look at most applications have a complex if-then-else logic, just kind of deciding what to do in the application. In Simple Workflow, we call that a decider, and we asked you to separate that out into its own component. Okay. The other concept here is that of workers. So you can think of workers as processes that are holding or that are hosting your activity implementation and your decider implementation. So these are processes that you can run on the same machine, you can run in the same GVM, or you can, it's really up to you how you want to distribute and scale that up. Usually, people run their activities in a larger set of machines because those are the heavy duty jobs, and then their deciders are typically running on a couple of machines. Both activities and deciders communicate through simple workflow. So there's no direct interaction between these actors. The communication mechanism between these components is tasks. So simple workflow creates a task and assigns it to a worker. The worker processes it and returns the result. So in this example, let's say when we want to process an image, your decider will get a decision task from simple workflow. And when it gets a decision task, it also gets this execution history that I talked about. And for a brand new workflow, that execution history is empty. So based on that execution history, your decider then decides what to do next. Right? So it's essentially an event log. It looks at the event log and says, nothing's happened, go download an image. Simple workflow creates a task to download an image and hands it off to an activity worker that's ready to process it. And it also records that in the history. And when that activity worker completes his task and returns a result, again, simple workflow will record that fact in the history. And this time it will create a decision task for the decider so that the decider can take another action, because now something has changed in their execution. So this process continues, and based on the history, your workflow keeps making progress until it reaches completion. The other thing that I didn't talk about here yet is those small boxes up there. These are task lists. You can think of them as queues. You can have as many of them as you want. And this is kind of our dynamic mechanism by which you can have various destinations for your tasks. So you can imagine that I create tasks for a specific set of machines because they are really beefy machines, and then I have another task list which is for some of the low priority tasks.
So,
okay.
Excuse me, Asad, I have a question. So how do you, so this is a public service obviously, so how do you deal with rogue activities or rogue tasks? So how do you deal with, me writing a very tight loop or something like that?
Right, so there are various mechanisms in the service backend that prevent you from run-of-the processes that may create a lot of activities and churn. So one of the mechanisms is that we have various limits in effect on the service, and they will prevent you to exceed a certain amount of throughput in creating activity tasks. And there are then hard limits on your workflow. A workflow can only have a certain amount of discrete events, and it can only have a certain number of activities open at any given time. So those limits are in place to kind of prevent that sort of a situation. And it's for real legitimate use cases, we have designed in place that allows you to kind of bypass those limits. So you can create things like child workflows and trees of workflows that can handle much larger.
Okay.
Okay, so a quick summary of concepts. Workflow, think of it as a multi-step background job. An activity is one step in that background job. A decider is a control flow. Task is a work assignment. Worker is a task processor. Task list is just a queue. And history is the distributed execution state. Okay, so I don't know how many people are familiar with AWS services, but in general, with AWS services, there are various programming options. So most services expose their APIs as HTTP APIs that you can directly use if you want. On top of that, we provide the AWS SDKs in various languages, so you can program against them in the language of your choice. And then what Simple Workflow does, which is a little bit unique, is that we also provide this convenience library on top of the SDK. It's called the AWS Flow Framework. And the idea with the Flow Framework was to make it much more natural and easy for programmers to write these distributed workflows. So remember how we talked about deciders and how they need to look at the history? And with the Flow Framework, you express your workflow in terms of classes and objects and methods. And under the covers, Flow Framework manages the details of looking at the history, calling up the right methods in your workflow, and so on and so forth. It also provides a number of kind of best practice features out of the box. So error handling is built in. you can handle errors that are originated in a distributed system from a remote component, just as it was like a local error. Other interesting thing that we provide is the ability to retry failed tasks that can be enabled through an annotation. The framework is open source. Right now it's available with the AWS Java SDK. So if you download the SDK or go to GitHub, you can look at the sources. And we also have a version now available in Ruby that we shipped earlier this year. Okay, so what does it mean to implement a workflow using Flow framework? So here are roughly the steps that you need to follow. The first thing you do is you define the signature of your workflow and activities, and that's done in the shape of an interface. So you define an interface which represents a workflow, and you have a method which is the entry point of the workflow. You define an interface or multiple interfaces where each method is an activity. Based on your interface, Flow framework will generate clients for you because these activities will be invoked remotely. We will generate a client that creates a task through simple workflow to be scheduled on the activity. Once you have the clients, you can implement a decider. The decider is just Java code. Right? It's any kind of Java construct that you want to use, object-oriented programming, fields, methods, whatever you want to use to implement the logical flow of your activities. And another thing that we provide here is support for asynchronous programming, and I'll go into more details on this shortly. So the idea here is it's pretty similar to futures in Java, which gives you back the result of the future result of a computation. The same thing here, when you schedule an activity that's going to run somewhere else, it may be months long, so we cannot give you a result back. What we give you back is a promise, which will become ready when the computation is done. Okay, then we implement the actual activities, the individual pieces of the process, and then we run workers to host them. Okay, so let's look at an example. Okay, so the first thing I want to show you here is how you would implement these interfaces. So let's go ahead and add an interface. So in this project, the only thing I've done is I've added AWS SDK as a library. Okay, so this is my workflow, and in Flow framework, you use annotations to declare workflows. Okay, so I've declared this interface as a workflow definition, and then I can define the entry point of the workflow. So when I start a workflow, this method will be called. So process. Which takes about, okay. And I mark it as the entry point of the workflow. Okay, so I need to provide a version for this workflow. You can use this version to create, if you want to modify the workflow, but you want to keep existing workflows running, you can use this version to create multiple different types of versions of your workflow. Okay, one more thing that we need to do here is provide registration options. So think of registration options as the default configuration of the workflow. So for example, when I run a workflow, there are certain default timeouts I can provide. There's a default task list I can provide where it will listen on for tasks. So this is the default configuration I can run. And here's asking me for the total amount of time that I want to keep the workflow on. So that's another mechanism where you can time bound the computation and not have a random process. So in this case, I say it can run up to 2 minutes. Okay? So one thing that I haven't done yet on this project is I want to enable annotation processing. photo so you can look at the flows of everything. I think I may have a file of this one.
So I guess this would be a good time to talk about how to debug something like this, huh?
Well, this is like compiling, right? So, well, I can show you the one I compiled. I think it's the package.
Just create one, yeah. Interesting.
Okay. So our annotation processor kicks in, and it's generated a bunch of clients for you. And if let's pick one of these clients. So for your workflow, it's created this interface, which kind of mirrors the interface that you define. And if you notice in this case, it's generating asynchronous APIs, because your workflow is an asynchronous program. And it's created a bunch of overloads. So it has synchronous and non-synchronous overloads for each one of the methods that you define. And then it has factory classes that you can use to instantiate our workflow, our client. Okay, and this is the actual client implementation. So you'll see we have three different types of clients here. There's the client, which you use to kick off your workflow from any Java application, which is the external client. Then there is client without any kind of fluff around it. And this one is used to create workflows from within workflows. And then there's a self client if you need to call a workflow from within itself. So three different kind of contexts where you can create workflows. Okay. Same way you can go ahead and add activities. Okay, and in this case, every activity is just a method. So for example, I can have the download activity, which takes the file and the bucket. And I can have another one, which is upload. It's thumbnail and upload them. Again, I need to specify the version. And I can have another activity which is create thumbnail. Okay. So let's go look at what's generated for us for activities. So similar kind of clients are generated for activities. Again, a bunch of overloads, but each activity gets both synchronous and asynchronous variants of overloads that you can use to call it. Okay, and the next step here is you implement these interfaces and use the clients to invoke activities. So I'm not going to bore you with typing anymore. You can look at the one I already implemented. So here's my workflow implementation. I use the generated client to call download. This gives me back a promise for the file that I downloaded. Then I called create thumbnail, pass it the result that I got back from the first activity. And then I called the upload, passing it the thumbnail and the bucket and the file. Okay? And this code is sequential code. Right? So the first activity will, the second activity will not execute until the first activity has fully completed. Okay, and my activity implementation is just plain Java code. And this is a Java method, and you can pretty much implement whatever you want in that activity. In this case, this is downloading a file from S3. This is creating a thumbnail, and this is uploading the file back up to S3. Okay, so the last thing that we need to do here is to implement the hosts. And we provide this workflow host class or the workflow worker class. And all it really is that you specify the task list that it should get tasks from. In this case, I defined a constant that it's getting it from. You define the domain within simple workflow. So domain in simple workflow is like a mini account within your account, which is a sandbox for all resources within that domain. And then you pass it the Java SDK's SWF client. So this is the low-level client that's in the SDK, which has your credentials. Okay. And then you start the worker, and the worker will then start coding on a loop. When it gets a task from simple workflow, it's going to dispatch it to the decider to process. Similarly for activities, the only difference with activities is that you actually pass it an object. And the reason we allow you to pass an object is that activities tend to be more stateful, in that they may have database connections, they may share a pool of network connections. So we allow you to pass an object. And then you just start it. Again, when the worker gets a task from simple workflow, it looks at the task type and then dispatches it to the appropriate method that you implement. So important thing to note here is that these are 3 separate executables. I can compile them and put them on 3 separate boxes wherever I want, and I can run them and label the work will get coordinated across all. Okay, so let's try one of these. Before I do that, here's my S3 bucket that I have an image. Okay, and this is my local store here on this machine. So I started the activity host, it's running. I can now go and start the workflow host. Okay, that's running. And this is a starter application. All it's really doing is that it's calling simple workflow using the workflow client and kicking off the workflow execution. Typically, this is your application. Like it's a web app, mobile app, what have you. From where you are actually creating a background job. Okay. So let's start the workflow. So I have print statements in my activity worker. As you can see, it went through each of the tasks in order as we expected. You can see on the local storage, it's converted the file to the thumbnail. By the way, I took this picture from my phone. We ran this a couple of years ago. Okay, and honestly, we should kind of do thumbnail
So question, so these apps ran locally on your local machine, but they communicated with the SWF service on the server side and told it to kick off and do stuff.
Yep.
Okay.
And you can actually go to the simple workflow management console and see what it did. So remember, this was the domain that I said. And inside this window, you can see it's one execution is just completed. So I can drill down into this execution. So in the console, you can see all the configuration that I set. And then you have the events and the activities. So the activities view shows you all the activities that ran, when they started, when they finished. And this is the event history that we talked about. So this is the detailed record of every event that's happened in your execution. So the first event is execution started, decision task was created, and then activities were created, more decision tasks were created when activities completed, and so on. So as you can see, we didn't need to process the history directly. We just wrote a bunch of code as regular Java method calls, and under the covers flow framework translated them to this history in simple workflow API calls to simple workflow.
Is that the extent of the event information that they have there? Or can you drill that into those?
You can
events?
drill down. So for example, if you click on an event, you can see more details. So let's, for example, try the workflow execution started event. So this one, for example, contains the workflow name, it contains the input that I passed in, and this is serialized JSON using the Jackson serializer, and a bunch of other kind of information. And I mean, the console itself has a bunch of other useful features, like you can search for executions.
One thing that's really useful here is for every activity or decision that started, the framework will post which machine it came from and which process ID it came from. Which, when you're wondering where is the process that died pretending to work on something, you can go find it this way. That helps a lot.
Yeah, for example, if you look at the activity started event, it's reporting the process, and this is the runtime. Okay. So in terms of the execution flow, I think most of this is kind of pretty obvious now after we look at the code. So workers, they pull simple workflow. And one thing that I kind of didn't talk about is that you can actually have a separate queue for each of these workers. So right now I was running it on one machine, right? But if I had like 3 different machines, the machine that downloaded the image should also be the one to process it. So in that case, what you can do is you can have host-specific task lists, and then that way, there's a shared task list, which is the first task, and after that, you can schedule the other 2 tasks to the host-specific task list to ensure that you're not downloading multiple times. So let's say you have 2 different workers. We started the execution. The first thing that goes in the execution history is just the input data. Task is created for the decider. Decider schedules download. Picked up by the worker, download is completed. Another decision task is created, which now says create a thumbnail. Again picked up by the worker and completed, and so on. And the execution history keeps on. Adding more events until the decider says I'm done processing, we can complete the execution. A few other features that are kind of useful when we're implementing these types of applications. First, we support signals. Signal, you can think of it as an asynchronous interrupt. So you started a workflow, and at that time you give it some input. But let's say something changed in your process. So the typical example is you are doing order processing and the customer wants to change your order. You can influence the workflow externally by passing it a signal. In your workflow code in Flow Framework, just as we have that execute method, you can have another signal method. And when a signal is received, Flow Framework will invoke that method, and at that point you can change the processing of the workflow. Child workflows that I talked about, the different clients. Child workflows allow you to create reusable workflows that you can share across different workflows and applications. And then another very useful feature is timers. You can think of it as mutable timers. One of the things that your workflow can do is it can ask simple workflow to start a clock to 10 days from now, and then it can go with it, right? And simple workflow keeps that timer running, and when it fires, it's going to create a decision task. And at that point, your workflow can wake up and do something. So this is very useful to do something like distributed clock.
Can can you, with the child workflows, can those be dynamically composed at runtime, as it were?
They can be dynamically composed. So and it can get pretty dynamic. The programming model that I showed you is kind of the go-to model that we have, but all of it is actually built on lower level abstractions that allow you to do things as strings. So you don't even have to implement or know the type ahead of time. You can just schedule the child workflow by its name, and that will work just fine. Okay, so now just looking at some of the things that we have done in the framework. Yeah, please go ahead.
Can you, if you don't know the type, is there any way to control, so if you have a sequence of workflows and one's going to be expecting a result of a certain type, can you get that information so you can control that, or is that?
Not through simple workflow, but that's typically what happens in those types of situations, is that it's a message or an input that's coming into the workflow externally. So it could be a message which says, I want you to schedule food, and here's the input. So that's really a contract that you will have with your application outside of simple workflow. But when we start the workflow, it expects input typically in a specific format. So it has to be.
So what if I have three different things I want to select from? So like some amount of dynamic choice inside my workflow of the path I want to take.
Right. So I mean, it's Java code. You can have any level of kind of control in how you define your control flow. You can use switch statements and based on whatever condition, pick one path or the other. You can also have like multiple of those things happening at the same time. So you can create multiple branches, and each one of them will be running.
Sorry, I missed the beginning of it. What about load balancing as far as resources for memory and CPU?
Right, so the model in simple workflow is a polling-based model. So your workers ask simple workflow for work, and you can adjust how frequently they ask. You can also adjust how many threads to use for polling, how many threads to use to process tasks. So depending on how heavy duty your activities are, you can dial those down. And if you want to add more workers, since it's a polling mechanism, it just load balances completely.
Well, that's what I meant, but across how many, across hosts and CPUs, I mean, you're going to have more workload that can be run on a single machine space, right?
Yeah, on a single machine, it's a thread pool that's used to process tasks. So if it's multi-core, then it will.
What about across machines? You need to work across many machines.
So like I mentioned, it's a polling mechanism, right? It's a poll-based mechanism. So if you have multiple machines, both of those polling simple workflow, each one will get a task. Yeah.
So managing the deployments and spinning up more machines, I guess that's outside of the scope of this framework.
Yeah, that's outside the scope of the framework. From Eclipse, you generate a jar file, and then it's up to you. We do have other
Doesn't like
services
integrate with Elastic Beanstalk or anything.
Yeah, you can certainly use those to do the deployment and manage the workers.
Yeah, we've got tooling in flight to make deployments easier.
So I was very pleased to recently hear that DynamoDB produced an offline version for development and testing. Do you have a offline version of this thing so you can develop it without actually being connected?
We don't have like a full version of the service. What we provide in the framework is a unit testing support. And what that lets you do is use JUnit to write unit tests for your design. So typically with your workflow, what you want to do is test the coordination logic, and you would typically mock out the activities. And activities, I would imagine that's your business logic that you will unit test separately. So there is support in the framework to let you do unit testing, and you can code against clients, but those clients will be short-coded and not creating tasks in the service.
So they would then return the promises and
Yeah. Okay. So, going under the hood, a couple of interesting problems that we have had to solve when implementing this framework. One of them is this is a distributed environment where tasks are running on different machines. The decider process needs to at times wait for the task to complete. Right? And you cannot hold on to a thread because the task may take forever. So how do you solve those problems? And in Flow Framework, we have built this asynchronous execution support, which allows us to you know, your decision, the decider itself is a single threaded implementation. So there are no multiple threads running in the decider because of this asynchronous execution support. So it's code that never blocks. We have provided some interesting kind of abstractions that make writing asynchronous code easy. I'll dive into that a little bit. And then the second problem that we have had to tackle is this execution state, right? How do you take the event history in simple workflow and convert that to objects which have fields and which have methods, and it just looks like a normal synchronous program. Okay? And the mechanism we use there is basically, you can think of it as how databases do transaction logs, right? Where if there's a crash and you recover, you read from the log and you recreate state. Pretty much that's how our decider works. It looks at the event history, starts executing your code, looks at the history and fills in the gaps so that the state is recreated locally. Okay, so why do we want to do asynchronous execution in our deciders? Well, it gives you higher parallelism without using multi-threading. We all know multi-threading can be challenging, very bug prone. You can easily do non-linear control flows. Asynchronous execution is usually done through callbacks, which are objects that you pass in to whoever you are calling, which means it's some state on the heap, so you can store it. And in a distributed environment where things are long running, you can store it, the process can go away, and at a later time come back and rehydrate it. And it's more deterministic. Like unlike multi-threading, where you have race conditions, if it's running on a single thread, it's repeatable, it's deterministic. Where asynchronous execution isn't that great is the programming mode. So in order to do asynchronous code, I have to create these callbacks. And that's a very weird kind of control flow. So if you've written any of these asynchronous programs, there's the code that's before the asynchronous call, looks very normal. And then you have the asynchronous call, which has this weird inversion of control, where I'm passing in something, and then that logic will get called somewhere else. Yeah. So, and if you do a lot of it, like if you have asynchronous within asynchronous within asynchronous, it gets pretty complicated pretty quickly. The other problem with asynchronous programming is the error handling, right? The caller who created the asynchronous task has gone away, no longer on the stack. So if an exception happens, how do you handle it? Typically what you do is you have another callback. So for example, in this case, you have this on failure thing. If it fails, we call this method, and it has to handle the error. But really, it's outside the context of the call. I don't know how to do finally. Things get messy. So the asynchronous programming support in Flow framework provides these constructs. First, it provides this promise object, and really it's a placeholder for the future result, much like a future is, but it's semantically different, and I'll show you how it's semantically different. And then we provide the support for asynchronous methods, and the asynchronous method is really a callback, but it behaves like a method call. So imagine you call an asynchronous method or an activity, it returns your promise. You can take that promise and pass it to another asynchronous method as a normal method call, and that method execution won't happen until the promise becomes ready. So from your point of view, the logical flow is whatever you expect it to be, but the actual execution is as if it was a callback. And then we provide this construct called try catch finally, and the idea here is to provide exception-based error handling for distributed asynchronous tasks, the same way that you have normal exception. And it also includes this support for automatic cancellation. So imagine you have 10 asynchronous tasks running, one of them fails, it will automatically cancel the others. Okay, so a bit more about promises. So, your classic hello world example. So at the top I have the synchronous code. This is when I would call two methods and I print out the result. Using futures, you can get pretty close to it with, where the result's not immediately available. But the problem with futures is that it's not an asynchronous construct. It's a synchronization construct. When I call get on a future, it's going to block. Right? So this thread is now blocked, I cannot do anything else. Now that's a problem with something like a decider. Promises look exactly the same as futures, you can call get on them, but the behavior is much different. If you call get on a promise and it's not ready, it's actually going to throw an exception. So that's not how you use a promise. So the correct way to use a promise is to pass it to an asynchronous method or an activity. So in this case, the code that I have below, I can have a print greeting method, which is an asynchronous method, as the annotation of it. And now it's fine. When this method executes, the promise would have already become ready. The framework guarantees that. So what happens is, when you execute this code and you execute print greeting, the framework simply creates a task and puts it inside in a queue for later execution. And then it keeps monitoring the promise to become ready. When the promise becomes ready, it executes the body of the method, passing it the parameters. This does create a little bit of kind of understanding challenge in terms of how your code executes and what the order of execution is. So here I have two pieces of code, one written using futures, another written using promises to kind of illustrate how this code executes. So I call these methods asynchronous methods, and I get the future and the promise back, call another one, and then I call the print greeting method. In the case of the future, that's an inline execution. Right? That method is on the stack, it will get called. In the case of asynchronous execution with promises, that simply created a task, put it aside, and went on, kept on executing. So now I'm actually on the print line. And it prints by. At some later point, the future and the promises become ready. And now, hello world is printed by the future guy because this print statement was unblocked. The futures became ready. And in our asynchronous case, now the print greeting thing became unblocked, so now it's executed. And you actually get the results which are in the opposite order. That's just a side effect of how asynchronous execution works. Now we've kind of already seen how you can sequence using promises in our.
If the promises were ready immediately, would you get the same order, or would the asynchronous tags?
You would still get the asynchronous execution order. You always create a task. It's either ready to be scheduled or it's not ready to be scheduled. So if the promise was already ready, it will be put in the queue to be executed immediately, but after you're done executing the code.
It's a code-rated multitasking locally.
And I'm guessing you can call an asynchronous method from within an asynchronous method.
Yes.
So this implies that like in this particular situation, it would actually end up using potentially three different instances of this class that would be spun up on potentially different machines.
Yes. So depending on how it executes and when the task complete, it can potentially execute in 3 episodes if you will. So the way the decider works is that it's going to try to execute your code as much as it can. And if it's sitting on promises that are not ready, and it knows those are executing in simple workflow, it will finish execution. So your instance goes away. And then at a later stage, when simple workflow creates another decision task, it will rehydrate the instance from the execution history, give it the additional promises, and it will make more progress. So think of it as running in episodes each time from the beginning and executing as far as it can. Okay, so sequencing, we have seen this before with activities. You can do the same thing with asynchronous methods. If you take the result of one and pass it to the other, you get that sequence in semantics. Okay, so
just to be clear, so it's the get name that will execute potentially on different machines. The asynchronous methods, they all execute on the same machine.
Yes, so asynchronous methods, think of them as local tasks. Activity methods are remote tasks. Yeah, because those you call through the client, so it's really on those levels of remote.
Okay, I'm confused.
Yes.
I was under the impression that if these 3 asynchronous methods are in a decider, then it would actually potentially unload the decider and could come up on a different machine.
Depends on what you're doing in the asynchronous method, right? So if your asynchronous method is calling an activity and waiting on a task, which is running remotely, then that would happen. That would happen. But if they are just like printing locally, then it would execute in one go. Because all those tasks, it depends on when the task becomes ready to execute. So think about the inputs that are being passed to the guy.
You have to have like a governing process though, right? I mean, sort of similar to the HDFS. Is this sort of modeled after that? HDFS MapReduce?
Not really.
Actually, MapReduce would be a subset of what this handles.
Yeah, but
So each one of these sequencing threads resides on a local machine.
it's single threaded. This execution will be single threaded. Right? The idea is when you call an asynchronous method, we will create a task to execute its call, right? And that task will execute only when its inputs are ready. Right? So if there's no remote calls in here, the inputs will become ready right away. Right?
So in this case, is get name, what type of task is get name versus the task that happens to execute locally like hello? In this current example.
In this current example, it's all local.
Yeah.
If I had, for example, an activity here, client.run activity, then that would be something remote. And if I return that promise here, then this guy is waiting on a remote task. And in that case, yeah, it will go out of memory. When the task completes in simple workflow, it will rehydrate, look at the result and print. Did that clarify? Okay.
I didn't say anything. I'm still working on the governing process.
The governing process in this case is the flow framework. Right? It's maintaining the list of tasks to execute. It's also monitoring all the promises. So
doing all
there is a dispatch loop under the code.
So I'm assuming that anything that the type in the promise has to be serializable.
Yes.
And is it just Java serializable, or does it have to be JSON serializable?
The default is JSON serializable using JSON,
Okay.
but it's a class you can override and provide your own. Okay. Yes.
That applies also for the exceptions, because the retries that is going to show you can use your own custom exceptions. Those also have to be serializable through the data converter that you use. There's the default one that uses JSON. You can provide your own, but that's going to be important there too.
Okay, so error handling. So we know how error handling works in the regular synchronous code, where I call E, I call B, I call C. And if C fails, the stack's unwound and my catch block is executed. Okay. So we wanted kind of this similar semantics for distributed and asynchronous tasks. So the abstraction that we have provided for this is this try catch class. And the way you use it is you create this nested instance of this class. And then you implement the do try and do catch methods. Okay? And there are various variants. There's another one with the find as well. So the way it executes is kind of similar to how a sequential program executes. And what it does is it basically associates to every task the catch callback. So in this case, the first thing it's executing is this do try method, which is yet another task. And it's saying that if that fails, then call this catch task. And then it calls A, it actually propagates that association down the chain. And then when A executes, then it associates the same catch block to B, and so on and so forth. And then when eventually this guy throws, it's going to call the catch block. So effectively it executes as if it was Java's try catch plan.
So okay, so the traceback then won't have any information about A and B in it.
It does. So the framework actually tracks the exception stack and it produces a synthetic stack. And if this was a remote task and running on a different machine, it will also include that. Like if it was an activity, you will have the complete stack trace.
Will you see what machine it was running on as well?
No, not in the stack trace. But you can always go back and look at the history. Okay, so the semantics, if an exception happens, those all tasks started in root try. You can try to cancel them if they weren't scheduled yet. If they were already being worked on, send a cancellation to the worker. Simple workflow supports a cancellation mechanism. When all tasks are closed, either completed or canceled, then call the do catch method and let it run to completion. And when everything is done, we call the do finally method, and there you can do any sort of data that you would typically do in a finally block. If the exception is not handled, it's propagated.
How exactly does a running task get cancelled?
So in simple workflow, your workers can report a heartbeat back to simple workflow. That's through the record activity heartbeat API. So that's a requirement for cancellation. The idea is that the worker will go back to simple workflow periodically and tell it I'm still working on that task. That allows you to make sure that the worker didn't die.
So in your worker code, you check has the task been cancelled?
Exactly. So if you report that heartbeat, it will actually throw a cancellation exception back to you in that case. Okay, so with asynchronous execution, really think of it as an execution tree as opposed to just a sequential execution, where one of your tasks can create multiple tasks, which can again then create multiple tasks, and so on and so forth. Now, if one of those tasks fail, that exception will be propagated up to its parent. The parent will then cancel any other task in that branch, and it's basically unbinding that branch of the tree. Exception is then propagated back up. Any other task at that level will get canceled. And let's say this was try catch, where I handled the exception, then the catch block is, or the catch method, recatch method is executed. And if the exception is handled here, we are done. And your workflow can then keep on executing. Okay, one last thing. So we talked about how we reconstruct state and how you have this episodes of execution. So here's an example execution and how the history looks like and what the execution actually looks like. So when we initially start executing the workflow, you have that dispatch loop that I mentioned that the framework is managing for all the tasks. The first thing in our example, it's created, actually it was a download image, but in this example I have a get image URL. And what you have, what the framework does is that it tells simple workflow to schedule this activity. And this activity is then recorded in the simple workflow history. When in the next iteration, when the activity has completed, simple workflow, the flow framework plugs in the results from history, and it tells simple workflow to create the next task. And this process continues. You keep on injecting results from history, and the workflow keeps on making more progress each time until it's run to completion. Okay, so just some lessons that we learned in no particular order. Some things we wished Java had better support for. So one of the things that bit us was type erasure at runtime in generics. If you have an activity that takes a list that has promises inside it, at runtime you lose that information. We have tried to solve that problem by providing another annotation that you put on the method, but it would be really nice if it just were out of the box. One of the things that we tried initially was to use statics to allow you to have your workflow code and your activity code all in one place. We also tried statics to provide some contextual information. What we found that was terrible for testing. For testing these types of systems, you want to mark out parts of your system, you want to mark out different activities. So we went back to a object and interface-based model.
Well, one of the things, you're looking at, you're doing this tech thing that's been done many times, which is manually rewriting code into continuation form for asynchronous. And yet, this has been a solved problem many, many times, right? I mean, this could be done through bytecode annotations and a bytecode rewriting scheme. In fact, Clojure, of course, has very nice, talking about pretty syntax, Clojure has core async, which does exactly that to rewrite. But the idea of having application programmers do the continuation rewriting, really, in 2013, seemed really backwards.
Does it look like we make you do continuation rewriting here?
Sure, because the try-catch finally objects, all that creation, the fact that you have to stub out the asynchronous task code into a separate method, all this can be inline and just rewritten through bytecode.
So actually, you can avoid, if you're just passing through methods, you don't have to do the asyncs to start with, and the rest, I think you're actually attacking Java, which we're not going to
I
stand
don't
here and
use
defend.
Java. I use Ruby and Clojure.
Yeah. So that's why
You
look
do
at the
this
look
kind
at
of
the
stuff.
Ruby one then. Look at the Ruby one.
Yeah, I mean, that's exactly the kind of feeling we had.
Like we
were-
suffered with it
It
too.
felt like we were implementing features that should have been in Java. So,
Impedance, mismatch,
That's why.
maybe language features.
Yeah.
Ruby, Clojure, but they can keep them in Java.
we also tried bytecode rewriting, and that has its own issues. Like, you have multiple tools that do bytecode rewriting, and that's an illness.
Well, Aspect J has a pretty solid framework. I mean, the thing is, if you try to do that from scratch, there's a lot of engineering involved in bytecode rewriting. So
It's very solid till someone else will also use Aspect J.
sure.
And that some of our customers are in that
Big
category.
pain point of ours.
Yeah. So
Okay, lambdas would have been nice. Fibers allow me to do kind of the things that, inline execution with asynchronous blocking semantics that look like synchronous code. If you look at our Ruby flow framework, that's blocking by default. No asynchronous semantics.
Which I think Groovy, not Ruby.
Okay.
This will also be slick and groovy.
Yeah.
We don't have to live with Java. Java plus plus.
So if Java had lambdas like several years ago, would you still have used this annotation, method annotation approach?
Some things could have been done differently.
Well, next year.
You mean 2020?
And we actually have a
It's
customer
common.
that's working on a Groovy implementation. I can't really share too much about that yet, but they built on what we've done in Java Flow and implemented in Groovy.
Yeah. You can have nice syntax.
Okay, nested classes were nice. We used them for try-catch finally, but the data nesting is kind of become pretty quirky with them. Okay, so just in general, and this is a lot of our kind of observation and also helping debug customer issues. Retries are a must-have. Exponential retry, we provide an exponential retry feature in Flow Framework, which is just an annotation that you slap onto an activity and configure it to do retries on your behalf. That's a must-have to use. Strongly typed interfaces work in most cases, but sometimes you want to be more flexible, like the question you asked. So we decided to provide both abstractions. Another thing that we found during the design phase was we want to be prescriptive. And that was, we had a principal engineer who kind of beat us to it. When you try to solve a problem and you find 3 or 4 different ways that it can be done in a language, the tendency is to say, well, let's support all of them. But a lot of times that's just more confusing for the users. Declarative programming style is good, it's concise, but there are use cases which are more dynamic. So in the Flow framework, for example, things like exponential retry are available as a declarative feature, but those are also available through regular method calls and objects. Same thing with asynchronous methods. Those are actually available as a class that you can create and through asynchronous methods. Take dependencies carefully, and I put it there for Asad. We had a lot of problems in terms of code generation not working correctly with Aspect J. Compile time tooling not working well with implementation process. Serialization can be messy, especially if you try to do cross-language. Now that we have a Ruby framework, and people try to write the activities in Ruby, in Python, and code in Java or another language, it can be pretty tricky. Use multi-threading only when needed. In our deciders, we only use a single thread, but that does solve a lot of problems. It makes it easy for regular programmers to write good code. And then use layer design. In Flow framework, we have built everything. All the abstractions are built up, and you can easily kind of remove any piece of the framework. So you can completely remove the type programming model, put on your own. A customer is doing Ruby implementation of it. So layered architecture usually helps in there. Okay, and that's it.
you have an example that shows how the retry stuff works?
I think I have the input. So here's an example. So this is basically saying use exponential retry, this thing fails, and then I can configure it with different things. So here I'm saying that the first time it fails, wait 5 seconds before the retry, and then try to do a maximum of 3 times. And there are other things that I can configure here. So I can specify a backup coefficient. By default, it's a coefficient of 2. I can filter the exception that I want to try and not to retry. And then I can expire after a time interval instead of number of times.
So I'm assuming that one of the key software technologies using here because of the interfaces is dynamic proxies to intercept and to replace the interfaces in actual implementations.
So a couple of different things. We use dynamic proxies in some places, like there's the exponential retry cabling that you can apply to like a client object. That's done through a dynamic proxy, but the annotations are implemented through SWF interceptors.
So then you said that an activity is single-threaded, right?
The decider is single thread.
The decider single-threaded. Okay. So maybe you didn't illustrate any examples there, but can your deciders or activities, can they have state?
They can have state, yeah.
That's
So
not
they
an
can
issue.
That's fine. You can have field and object, complete object-oriented programming. You have to be careful in the case of activities because it's a single object that's processing multiple activities. So you have to have any shared state.
Oh, okay.
It will be left over after the activity is done.
Okay.
And for the workflow, if you kind of like populate the state as you go, then the replay will repopulate the state, like rehydrate the state of wherever else it's picked next. So, for instance, the dynamic scheduling that you were asking about earlier, like typically signals would add something in a work queue to either add or cancel something from the work queue, which is actually an instance field, part of the object that's rehydrated and manipulated as you replay the history.
So unfortunately, I don't have a slide here with useful links, but if you search for recipes, flow framework recipes and samples, you'll get a lot of good code snippets that show a lot of different use cases.
What about performance? Are there tools? Is there support in the framework for tracking, performance? I mean, understanding, of course, that there's a lot of asynchronous processing going on here. That has its own set of challenges
Right.
in terms of tracking,
Yeah.
stuff like that.
Right. So we don't have any tools that let you do performance tuning of something like a decider. That's typically not your bottleneck. The decider task usually run in like seconds. Your activity code is really business logic, so we should profile it the way we would profile it in Java program. What you do want information on is what sort of the overall execution metrics, like how long did my execution take, are they getting slower, which workers are running slowly. We don't have direct metrics for those available yet, but at some later point in the future, we'll
With Amazon Web Services, often you care less about the performance, but about the cost. How much is it costing you? So that could be neat if you saw like this workflow execution used like $5 worth of the Amazon Web Service resources.
like a cost profiler.
Yeah.
Which one of my original tasks is costing me
Right.
so much money?
That's not a problem to solve.
Like be able to go ahead and schedule quotas.
Okay. Any other questions?
All right. Yes. Well, thank you very much, Asad.